Hi. In the last few lessons, we've been taking a look at central tendency, which gives us kind of a typical central number for a data set, like what kind of value we would be expecting. Something just as important that though is something called spread. And basically we want to take a look today at how to measure spread. And that just tells us how far apart the data points are from each other. So just as an example, if you think about the average grade 11 student at your school, the average grade 11 student is probably around 16 years old. However, the average student in your entire school is probably also around 16. So they have similar central tendencies, but your school age for your entire population, all your students at your school, would vary quite a bit more than just the age difference in the grade 11s, which are all going to be 16 or very close to 16. So the idea here is that knowing the mean is one important thing, or knowing the central tendency, I should say, mean, median, or mode. But knowing the spread is just as important. So we're going to take a look at a couple of ways of measuring spread. The first method we're going to look at is called range. It's the easiest and arguably the most useless um, to calculate. Well, easy to calculate, almost gives us no information. Something called quartiles, and then the interquartile range, which tells us a little bit something more, and something called standard deviation, which is by far the most useful measure of spread that we have. So the first one, this is going to be an extremely short topic because honestly, range is just telling us what is our highest value minus our lowest value. So what is the range of values that we can take on? So for instance, if we were looking for the range of ages in a high school, usually high school, about the youngest person we'd have is 12. The oldest person we'd have is about 20, maybe 21, depending on, their background. But let's say 20. So the range would be 8. 20 minus 12 is 8. So it's just saying that there's about 8 years difference between the lowest number and the highest number. I think you can imagine that if you have any kind of outlier in your data set, the range is going to be so skewed that it will give you almost no information. So just an example, when I was in high school, um, that was back before we had specific adult day schools. And I remember there was one class that I wasn't in, but a friend of mine was in. I think it was a grade 11 French class or something like that. But one of the guys in the class was like 45. And now if you think about that one person being added into the high school student mix, that would drastically change the range from 8, going from 12 to 20, to basically like 33, going from 12 to 45. So because of that, range tends to be pretty useless. Quartiles. Quartiles are going to help us out a little bit, along with the interquartile range. We have to understand how quartiles work before we get into interquartile range. And basically, if you understand how a median works, quartiles are very straightforward. A median is a number that, or a place that sets our data set in half, kind of say this is the bottom half, this is the top half, and the median is the middle point, if there is one, or the middle 2 points if there's an even number. Quartiles are basically taking the median and then taking the median of each half to give us a first quarter, a second quarter, and a third quarter. So instead of a middle point, which is actually equal to Q2, the middle point, Q2, and the median are the same thing. Whether you're halfway through the data set or 2 quarters, same difference. Q1 is the median of the first half of the data set. Q3 is the median of the second half of the data set. And then interquartile range is kind of like range, but instead of going with all values, we're just going to do Q3 minus Q1. Why is that so much better? Well, what it's basically doing is saying, what's the range of the middle half of the data? If we throw out the top quarter and the bottom quarter and just look at what's left, um, that's the interquartile range. And the reason that that tends to be much better is because if you have outliers, it's highly unlikely that more than a quarter of the data will be a high outlier or a quarter of the data will be a low outlier. So it's a much more narrow focus, but it does give you more information about the data set. We are going to be doing all these things as examples in just a moment, but we're going to kind of do them all at once since they're very related. The last thing I want to look at is a box and whisker plot. Now the picture of the cat version on that on the left is is just there for pictorial purposes. Um, the reason it's called a box and whisker plot, if we look at the picture on the left, is that we have a box in the middle with a line down the middle of it, and then we have two whiskers, one going off of each side. And what the box represents is the interquartile range going from Q1 to Q3. The line down the middle of the box represents the median, and then the whiskers represent the minimum point and the maximum point. So the box is the interquartile range, or all the values of the interquartile range, and the whiskers are the max and mins. Now, how you actually draw these is a little bit of a artistic interpretation. So you'll notice that the top picture has dots in 5 places. I tend to draw something similar to the ones on the bottom, where we draw basically 5 lines and then connect the middle 3 into a box, and then the outer 2 get connected with whiskers. Now, you may also see vertical versions of these. So instead of going horizontally, you might see vertical ones. They tend to be fairly common too. We'll stick with the horizontal, but just so you're aware that these can exist for, well, in a whole bunch of different ways, and you might recognize them. What box and whisker plots are useful for is if we're comparing two data sets that represent sort of the same thing, but are not identical, obviously. So in the example here, we have student marks in 2 classes. We have Mr. Scarlett's class and Mrs. Plum's class. And what it's doing is showing how those 2 data sets compare to each other. So for instance, we can look at this and say, well, Mr. Scarlett and Mrs. Plum both have, their top student is about the same. Mr. Scarlett, his lowest student is significantly better than Mrs. Plum's. Um, I think I just married them. Um, Mr. Scarlett's worst student is better than Mrs. Plum's worst student. He's got a much higher minimum than she does. However, she has a much higher median than he does. So there's a whole bunch of information that I think you can get off of just reading those 2 box and whisker plots and comparing them to each other. And when I'm doing stuff, for instance, trying to compare how my students perform year over year in the same course, and I did this a few years back for data management. I looked at about a dozen data sets, a dozen different classes, and did these for them. And you can kind of see how the whiskers kind of jump around a bit, but ideally the box part doesn't change too much. Okay, so now that we've seen what those are, let's actually try to apply them in some meaningful way by doing a question. And we'll start off with, we've got 2 data sets here. And this, by the way, is real data. I didn't collect it, but I found an online study that someone did measuring the time it took men and women in a mall to use the bathroom. I've got to be honest, I had to ask myself a whole bunch of questions about how this study was conducted. I'm like, is there just some creepy guy standing outside the doors of the bathroom timing people when they go in? And yeah, how do you deal with that? So anyway, I was actually a little surprised by the results, because it looks like women spend less time in the bathroom in a mall than men do. And I'm just interesting. Anyway, so for the top data set, we're looking at women using the bathroom, and the lowest time was 48 seconds. The highest time was 114. So if we want to find the range, and I'm going to just do a little bit of math right above. It's 114 minus 48, and I think that's going to be 66. So it has a range of 66. And by the way, these values do have units as well. We usually just don't bother writing them in. Since this was the time for women to use the bathroom, it actually doesn't state seconds, but it is in seconds. The range would be 66 seconds between the lowest and highest. Now, I will also point out that this is a pretty small data set. The real data set was actually much larger, but for our purposes, I didn't want us to be spending, 20 minutes counting numbers and so on. First quartile, second quartile, third quartile. Trick to this is you're always going to do your second quartile first. You're always going to find your median before you find anything else. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. And the middle one is our median. It's an 82, and median and second quartile mean the exact same thing. So the median time to use for women to use the bathroom was 82 seconds. Now what we have to do is do the median for the first half and the last half of the data. Here's the trick. 82 is neither on the left-hand side or the right-hand side, so we don't consider it to be part of either data set. We basically throw it out and just look at the four numbers to the left and the four numbers to the right. So on the left, we have four numbers. The median here, there won't be one single value because it's got an even number of data points, but it's going to go down the middle here. And basically, it's going to be halfway between 63 and 73. Which are 10 apart. So 5 above 63 is 68, 5 below 73 is 68. So our Q1 is 68. Q3, same idea. It's going to be halfway between those two data points. And so once we've removed those, or sorry, once we've looked at the halfway point between those, they're 6 apart. I think you'll agree that it's 88. And then our interquartile range will just be the 88 minus 68, just like the range, except we're not doing it with the max and min, we're doing it with the third quartile, and this is the first quartile, and we get an interquartile range of 20. So that means that half of the women that went into the bathroom came in within a 20, or came out within a 20-second window of each other, time-wise. So that's a little bit more useful than the actual range. Keep in mind the actual range, if someone in there went in and had like a medical problem and collapsed and it took them an hour to have the paramedics come and take them out, that would grossly affect this study. And we don't want someone's medical condition to ruin our science. So getting rid of those outliers is always a great idea. Now we can do the same thing, time for men to use the bathroom, and I won't do too much explanation here. That's just going to be 200 minus 54 is 146. Now here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. So there is no central one. So I kind of draw a little tick mark down the middle. And our our median will be halfway between 121 and 125. So that's 123. And now we have 5 data points in the first half and 5 data points in the second half. So we circle the middle ones. So Q1 78 and Q2 is 150, or sorry, Q3 is 158. Interquartile range is just the 158 minus the 78, which is a difference of 80. Okay, so we can see that despite the fact that men do seem to use a little more time to go to the bathroom, their median is a little bit higher. It's actually significantly higher. It's about 50% higher than 82. Their spread is about 4 times what it was for the women. So interesting deductions to be made there. Okay, so now for the box and whisker plot. So what I'm going to do is take the numbers, basically the minimum, the 3 quartiles, and the maximum, and draw little vertical lines above the number line there, and just try and see what the data looks like. So for women, the minimum's 48. I'm going to put that about here. And if I look like I'm a little off, don't be too upset. It's just I've got to unfortunately work on a funny angle with my tablet here when I'm drawing. The 3 quartiles are 68, which go about here. 82 there, and 88 about there. And then the maximum is 114. So again, don't yell at me. That might be a little too high, but it's in the ballpark. Okay, and then I connect the middle 3 with a box and the outer 2 with whiskers. And if you use dots instead of lines, you've got to kind of use lines for the box part, but if you use dots for the whisker, that's fine. But this is the way that I will draw them. Okay, for men, similar idea. We have 54 is the minimum, and then our 3 quartiles are 78, 123, and 158, and our maximum is 200. Okay, connect the quartile ones to represent the interquartile range, and then connect the end 2 with whiskers. And we're done. So there's a nice pictorial comparison of the men and the women bathroom times. And we can see that in almost every metric, the men take longer than the women. Okay, let's talk about our last method of measuring spread, technically the last two. I'm just going to touch on variance because it is so related to standard deviation, it's almost not worth mentioning. The only reason I'm mentioning is because it comes up in one little application that we have to cover a little bit later. And I'll remind you of it when we get there. But standard deviation, which is going to be the lowercase sigma symbol, that's that thing on the left of that equation, is going to be equal to the square root of the sum of the differences between each data point and the mean, all squared, and divided by n. Now, honestly, this is more a chore in trying to make sure that you understand notation and bed mass than anything else. Okay, so let's just break this down and see if we can do this nicely, because if we actually try and write this equation out in its long form, it takes forever. It takes a huge amount of space to write. So we're going to take a little bit of a shortcut. If I look at this, the top part there says x minus x bar squared. X minus x bar is each data point minus the mean, and then squaring it squares that number. The reason the square comes in handy here is because it means that the sign of x minus x bar doesn't matter. So if, for instance, x minus x bar was positive 2, that just means the data point was 2 above the mean. Or if it was negative 2, which means it was 2 below the mean, once we've squared them, they're 4. So we don't even need to think about whether they're above or below. We just need to say how far are they apart away, or how far apart are they from the mean, square it, add those numbers together, divide by n, which is the number of data points, and then square root. Okay, I'm going to try and leave that on the screen just so you can see it while we're actually doing this calculation. And one thing that we're going to have to do before we actually apply that equation is figure out what the mean of the data set is. So I'm just going to do that really quickly over at the side here. It's 158 plus 146 plus 128 plus 149 plus 119 divided by the number of data points, which is 5. And just give me a moment to plug that into my calculator. If I recall, it works out nicely, but we'll see. Okay, so that's 700 divided by 5 is 140. Okay, so now if we want to calculate sigma, the standard deviation, we go through here and just say, how far is each of those data points away from our mean, and then square it. So I'm going to actually write it out this way. Now, this is where, again, it takes a long time to write it out. If I write out 158 minus 140 all squared plus 146 minus 140 all squared. So I'm going to just jump that step and say, for each of those 5 points, how far away are they from 140? So the first one, 158, is 18 away from 140. The second one, 146, is just 6 away from 140. The third one, 128, is 12 away from 140. To be really technical, it's minus 12, but since I'm about to square it anyway, I'm not even going to bother worrying about writing down the negative. 49 is 9 away. And 119 is 21 away. Same thing, it's a negative, but it's about to be squared. Now, I don't know why students with this specific equation seem to do this a lot, but that square root sign always seems to creep up and only square root the top part. It's got to square root the top and the bottom in this case is 5 data points. Okay, now that we have that, I can scroll up a little bit and lose the equation at the top. I don't think we have to worry too much. Just give me some more room to work. Okay, and now just to save us a little bit of writing, I'm going to actually do this math in my calculator, at least the stuff inside the square root. So that's 18 squared plus 6 squared plus 12 squared plus 9 squared plus 21 squared. And actually, I will do one more step here. It's the square root of 1026 divided by 5. And one of the reasons I'm doing that is just to remind you that that square root has to actually take the square root of the divided by 5 part as well, not just the 1026. So 1026 divided by 5 becomes the square root of 205.2. And then when we take the square root, the standard deviation is 14.3. All right. So just to recap a couple things and point that out, because the math is usually what students are so focused on that they forget what it is we're actually doing here. And the truth is we're finding a standard deviation, which I still haven't really explained what that means. A range makes some physical sense. It's the biggest value minus the smallest one. It's how far apart they are. Interquartile range kind of makes sense. It's getting rid of the top quarter and bottom quarter of data and doing the same thing. Standard deviation just seems to produce a number. And I will agree with you right now that a number that is almost impossible to make any physical interpretation of. For now, let's just say that the bigger this number is, the bigger the standard deviation is, the more spread out the data is, and the smaller it is, the less spread out the data will be. And we'll see over the next 2 lessons, we'll get a much better feel for what standard deviation represents. Again, it's not really a physical measurement, it's just kind of an idea. But the important is we like to know how many standard deviations something is away from its average or its mean. Okay, looking at this next data set, which is the body temperature of females. I don't know if it's important that it was females, but that was the data set that I happened to find. Oh, we didn't even really talk about this. Top one was the weight of babies at birth in ounces. Anyway, units don't really matter. Let's try this one. Body temperature females in degree Fahrenheit. So same thing, we're going to have to figure out what our mean is over at the side here. And I'm going to just speed up the process and type it into my calculator. We have 98 plus 98.1 plus 98.2 plus 98.4 plus 98.8. And that gives us 491.5 divided by 5 is 98.3. So 98.3 is our average temperature. Now each of these, write down sigma equals square root, and again we're going to do the difference of each of the data points, how far it is away from the mean. So 98 is 0.3 from the mean, and square it. 98.1 is 0.2 away from the mean, and square it. 98.2 is 0.1 away from the mean. The next one's also 0.1 away from the mean. Direction's different, but again, since we're squaring, the plus or minus doesn't matter. And the last one is going to be 0.5 away from the mean, divided by 5 data points again. Okay, so I'm going to punch this number into my calculator, and I'm going to do this all at once for this one. 0.3 squared plus 0.2 squared plus 0.1 squared plus 0.1 squared plus 0.5 squared equals, you know what, actually I'm going to write down some more numbers just because if anyone's looking back and they want to verify what I did, they can, especially if I make a mistake, which is always possible. Okay, so the squares of everything at the top work out to be 0.4. 0.4 divided by 5, 0.08. And then the square root of that is going to be 0.28. And at some point we're going to have to round off. I think keeping one more decimal place is enough. So I'll say 283. Okay, so as predicted, a much smaller, much closer packed group of numbers. So all these numbers are very close to each other. The highest is 98.8, the lowest is 98. They're pretty close. Is going to have a fairly small standard deviation, uh, just a little over a quarter. All right. So a little note here about standard deviation, variance, and a few other things. There's more detail than what I am covering here, and I'm purposefully overlooking the details of some of these equations. If you're interested, there is a video I'll post, or you can Google it or look at the link down there, but I'll post it as well. And you can follow that and it will explain some things. Now, for those of you who are really intrigued by math, I would recommend watching it because it's something that's quite interesting mathematically. For those of you who are maybe struggling a little wee bit with this concept, I would maybe recommend you don't watch it because it may just confuse you more. I will point out that if you are going to go on to a college or university course in statistics, you're going to see these more advanced things later anyway. For now, we're kind of purposely dumbing them down just a pinch to make them a little bit easier to understand and digest. So I'm going to stop there, and we'll continue our next lesson by looking at, well, a particular measure of spread, or at least a particular spread that is really useful to us and takes into account standard deviations. So we'll talk more about what that does next time.